I'm going to talk about on several timescales, and I'm trying to focus it really because part of the Cabot's brief is to actually think about uncertainties and so on. So I'm going to talk a little bit about risks that we have in government, how we deal with it, and then I want to sort of talk rather more generally about what's happening to the world, really. So let me jump into that. One of the sort of problems of my job of the last 5 years is that pretty much any audience that I speak to knows lots more about the subject I'm going to speak to than I do. And I have to say that this is no sort of deprecation of this audience to say that I feel slightly less nervous talking to you this afternoon than I did when talking to some people in the physics community about how nuclear fusion could be generated by the use of lasers. This was slightly outside my domain of information, but so thank you. Let's jump in. The way that government deals with risk, and first of all, the government has a thing called the National Risk Register, and that does two things. It looks at the likelihood or the chance of an event happening, and it looks at 5 years, and it puts these events on two axes. Essentially, on the bottom axis is the likelihood, and on the vertical axis is the impact. And I'm going to talk about some of these issues and how we actually deal with them in the first bit of the talk. To give you a clear idea of it, and it's illustrated in red on the right-hand graph, is that pandemic influenza is seen as not only the highest likelihood risk, but also the one with the largest impact to affect society as we know it. And I'll come on to that in a moment. There are some other risks, and other risks here are things to do with, for example, severe space weather, something that you will be less familiar with in pandemics, volcanic eruptions, and indeed coastal flooding. And so this is in a sense the way the government plans 5 years ahead and thinks about how it can actually mitigate, prepare for these actions, have some degree of resilience to it, and making certain that we actually have planning in place that we can deal with it. Now, how do we actually assess these risks? And risks are of different sorts. The ones I'm going to talk about this afternoon are very much the risks that come from natural hazards. So we have information from historical evidence, weather forecasts give you predictable events, we have expert advice. In the world of security and counterterrorism, we also have to be thinking pretty hard about the potential threats that terrorists can actually provide. And there, as opposed to using historical evidence, we use other factors. We think about plausibility, intelligence about capability, intent and vulnerability. And these are the sort of things that, in fact, in our national risk assessment, there is essentially divided into two things: the hazard and the risks that come from natural events, but also those that come from actually the impact, the threat that actually comes from essentially terrorist-associated groups. And of course, there's sort of wider ones where we actually think about the potential of state intervention too. And one of the ways that we try to assess the likelihood in these two ways. Clearly, the threat issues that come from counterterrorism are slightly less grounded in science, in fact massively less grounded in science, than those to deal with historical events and the likelihood of events. But in terms of impact, the sort of things that we have are what is the likely impact in terms of fatalities, casualties, social disruption, economic effects, and psychological ones. So that, in a sense, is the two sorts of pieces of evidence that go into developing the National Risk Register. Now, as I said, one of the first things, the most concerning threat, and this I inherited when I went into government, was the threat of some form of pandemic. And influenza is one that we have a history for. This gives you an idea of the different strains of the influenza virus that have actually given rise to quite significant epidemics and numbers of deaths. The Russian influenza outbreak in the later turn of the 19th century was probably the first one that has any form of recording of the effect. A Hong Kong influenza just around the turn of the century, and the largest that we've actually seen, which is the Spanish influenza, which occurred at the end of the Second World War. And of course we've had others since, the latest being the swine flu. I think just to give you, focusing on swine flu, and I'll go on to that in a little bit more in detail, you'll notice that each one of the previous epidemics has actually got some form of geographical reference. And the very first phone call that came to me when the swine flu came out was a request from the farming community to say, could we not get this designated as Mexican flu? Because the pig industry are extremely worried about this being called swine flu. So, such is the life of the chief scientific advisor. And indeed, the swine flu epidemic was really quite intriguing. And when I say we were enormously lucky, I truly mean this. It was first noted in Mexico in early April. And by the first couple of weeks of May, it was in about 40 to 50 countries around the world. And the early information that we were getting was quite a lot of mortality in groups, pregnant women, rather tragically, not so much the one with the very young and the very old, but there were quite a lot of deaths associated with this influenza, and we knew nothing about it. It was a genetic composition which had not been seen before. We had not expected it. The worry we had was that this was going to be somewhat similar to bird flu, which actually had not actually moved from human to human transition. So once we got this influenza epidemic coming with swine flu, we had to take real care in dealing with it. And here we come to one of these sort of actually, part of my job was quite sad, but there are occasionally light moments in which the then health secretary said, well, you can say this for swine flu. It managed to close Eton College, whereas 100 years of socialism has failed to do so. And actually there's a case, because actually we learned a lot from Eton College, because Eton got swine flu in a big way, and the college was closed. A number of staff and lots of the pupils actually went down with swine flu. But we were able to actually go into the college and take blood samples and find out what proportion were actually showing symptoms and what proportion had the disease. And in fact, for every person who actually showed symptoms, 8 people had actually had the virus with no symptoms at all. And that clue, which didn't come until late July, gave us the clue that we actually did not have a real problem on our hands in terms of something that was terribly serious. We have a mortality rate of people who had the disease, therefore, of less than 1 part in 10,000. So we were incredibly lucky, though tragic deaths occurred, and we dealt with the disease. But to give you a flavour for it and why we think this is something that we continually need to worry about, is that of the people who get bird flu, transmitted not human to human, but from birds to humans, 60% of the people who get it die. So we were on a 1 in 10,000 death, whereas it's 60 in 100 were the things that we were really fearing. So that was one of the worries we have, and it's why it's still right at the top of our national risk register, with the highest likelihood and the highest impact. One of the things I'll take you through is that you can see the relative frequency of this disease. So part of the job we have to do is to say, what is the probability of this happening? But obviously the severity is highly variable. And we have to worry because actually there's a lot of disease out there. And this gives you a pattern from 1980, so the last 30 odd years or so, in terms of different human and animal diseases. Many, I won't go into detail, it's rather a busy slide, but it gives you a feeling for the number of new diseases that are actually emerging. And only in the last 2 years, we've had the Schmallenberg disease, which affects cows and sheep, And we've actually had, and I think there was something in the newspapers this morning about a completely novel coronavirus, which actually is killing a large proportion of people, but is currently not contagious. So the variation that we have to expect is going to be enormous, and we have got to expect new diseases will come, whether it's new diseases of humans or animals, or as indeed I've indicated at the top here, also very new diseases of plants. And Paul referred to the disease of ash trees that came in during the last year. So this is this, and one of the problems we have is our vulnerability has gone massively up. One consequence of the small world we live in, this shows the density of air travel. And you can actually get a very good approximation once you knew that the disease, that swine flu started in Mexico and spread to the USA, of quite where it's going to occur afterwards. The pattern of air travel gave you a very good idea of where it's going to come next. And this is a consequence of the small world we live in, that there are going to be all manner of that things will not remain isolated. The expectation is a new flu virus will develop in Southeast Asia. That's the expectation. We were totally wrong. It developed in Mexico, but the expectation is that this would be around the world pretty much within a month. And SARS, which which occurred in 2005-06, was around the world in about 3 or 4 weeks. And these things are going to happen, and we're going to have similar issues in terms of animal diseases. And there are new animal diseases coming and new human diseases coming the whole time. So this is going to remain high up on our national risk register, and we need to be thinking about ways to actually mitigate it. So that's, as it were, the biggest one and a big worry. Now, the one we got here, and there's a number of people in the audience here, I can see Willie Aspinall here, and helped us with this. We had the problem with a volcanic eruption in 2010. First thing, this was an enormously irritating disaster that I had to deal with, because I do not believe any human being, unless they were born in Iceland, can pronounce the name of the volcano. So a name that has something like 17 consonants to one vowel is actually quite challenging for anyone except for an Icelander. So the first thing about it was that I had to learn to sort of refer to this volcano or the volcano in all interviews on the radio and the TV. But this one is a kind of odd one, because first of all, we had, there's a truism that there are a lot of volcanoes in Iceland, and we got it wrong, really. But this was really quite problematic. We reckon £1.5 to £2.5 billion was actually cost. 10 million travellers were affected, most of whom wrote to me complaining. And there was a real problem, and we probably should have thought about this rather better, because we could have predicted this. We really got it wrong in terms of the National Risk Register. Give or take, the historical eruptions in Iceland occur about 25 per 100 years. If we go back substantially into history and looking at historical records and so on, so give or take one every 4 years. And there's some periodicity here which complicates it, which is shown in the bottom graph. But we had the situation that we really should have done it. And there are a lot of volcanoes out there in the world, and the top right graph shows it. Most of them, I should point out, are pronounceable. I can pronounce Katla, I can pronounce Laki, so if that comes along, let it be. I have no concerns with it. At least I can pronounce the damn thing. But we put this here in terms of the analysis of what would be the likelihood and what would be the impact of these. So that was, in a sense, what happened. We should have had it in the risk register. We didn't. And it caused enormous disruption. But actually the disruption was caused not so much by the volcanic eruption itself, but by profound stupidity. And the profound stupidity was to do with the regulations. This was some mapping that was done by the Met Office and the Aviation Authority. And the reason is that the regulation because there had been problems of planes flying through ash, which had then had engine failure, not many, but there had been. The regulations were framed in saying, if there is any ash in the air column, you cannot fly. So you cannot fly through this, whatever it was, tiny, tiny concentration or very significant. And that was the actual regulation. And that was the regulation that was first brought in to actually close down most of the airports in northwestern Europe and the UK. Profoundly stupid regulation, because the basic physics says, what's the concentration, how long do you fly through it? Because that's going to be the genuine risk to the planes. But it was there. And we realized that as soon as we started dealing with it. I'll come to the SAGE process in a moment. But I was asked to chair the Science Advisory Group in emergencies. I co-opted experts on volcanoes, Willie Aspinall, Steve Sparks from here, and Matt Dawson, and others, to actually look at how we could actually predict it. And what came out as actually was the predictions weren't that bad. Important to get information about how much ash was being generated by the volcano, how high it was going, linked in with Met Office maps and so on. But that we were able to actually say, look, these are the zones. But of course we had the profoundly stupid problem that any ash was not allowable. Now, how do we deal with that? Essentially, so the Met Office in their models had got a model which said essentially 10 to the minus 18 grams per meter cubed was seen as 0. Now, and we wanted to move back from that. So you can imagine the ease with which I was able to explain to the cabinet that actually we were going to redefine 0. And that we were going to redefine 0 as being from 10 to the minus 18 to 10 to the minus 16. And this was challenging, I think is fair to say. But we managed to do it, and that meant that we moved from the areas that were shown in black to the areas that were shown in grey, and allowed us to essentially reopen the airports. And the regulations have been improved subsequently since. The problem, though, is that actually the explosive eruption that we had in 2010 occurred, of course, to do with a massively increased vulnerability. The expansion of air travel in the North Atlantic has been enormous. Therefore, and the skies in the Northeast Atlantic are, of course, extremely crowded. And this meant that the vulnerability went up. But that volcano is not the only one likely, and indeed the one that we have on the National Risk Register that really worries us is something that occurred about 300 years or so ago, 350, was the eruption of Laki. Note I can pronounce it. This is an effusive reaction which puts a lot of noxious gas, in particular sulfur dioxide, into the atmosphere, produces acute health effects. Lots of people died in the late 18th century. Big problems disrupting crops. It lasts for a long time. And it still has a 4% chance of happening in 20 years. So this is something that we really do worry about. And this will be a significantly more problematic event than the one that we got from the volcano. You'll notice I've also done some calculations, which I'll come back to in a moment. The chance of no further eruptions in 20 years is less than 1%. So this is something that's pretty likely to happen on some timescales. The other one, which you may know less about, because we haven't had an event, is severe space weather. Effectively, what happens in space weather is that you get sunspot activities, that you get and that can produce a whole series of things, solar storms or coronal mass emissions, essentially producing either intense solar radio bursts or electromagnetically charged particles coming to the Earth. The graph on the right-hand side shows something that came out from a sunspot on the Earth last year, about just over a year ago, in which we were incredibly lucky because actually it missed us. The emission comes out, it basically hit the Earth a glancing blow. If it hit us direct, we would have a real problem. And the problem is that it's so I'll go back to the frequency, and this takes you there. How often can we expect these sorts of events? They're linked with the solar cycle. They are linked to, and operates typically on about an 11-year cycle, and you get major storms quite often correlated with a predicted maximum. This slide was done in, came from a chap called Mike Hapgood, who wrote early in 2012. Mike is at the Rutherford Appleton lab, and I looked in a jaundiced way at the likely predicted maximum of solar activity, which coincided with the opening of the Olympic Games. It did not happen, so my prayers for intervention worked. So that's the thing that we have to deal with. And we need to be thinking about how we deal with it, because the disruption from space weather is on several forms. First of all, big problems with airlines and big problems with the GPS signal. And the GPS signal is particularly important because it, in fact, allows from the financial markets through to the rest of industry to have a very good timestamp, to have an idea of what temporal sequence is. Very important. If you don't know when a particular financial trade has been done, pretty difficult to get some proper regulation of it. Regularly, several times a year, you get a diversion of flights which are around the foal because there's an interference with high-frequency communications. And also there is the potential with a coronal mass emission or a strong magnetic storm that you will actually get a disruption of the power grid. And the latter one I'll come on to in a moment. I think the problem here is that, first of all, GPS, very important, but you can do things with satellites. You can think about alternative time monitoring. You can think about moving satellites into less vulnerable orbits. You can think about turning them. Airlines you can divert. But power is a real problem because the disruption to the power grid depends on the magnetic field that is associated with the coronal mass emission. Now, what about the early warning of this? Well, we know that there's going to be, we have satellites which will tell us that something has happened on the sun, something is heading towards us. We have about a 17, 18-hour time delay, knows something that's going to be hitting the Earth. We also know that whether an increasing accuracy from our satellite monitoring of whether it really is going to hit the Earth or miss us or give us a glancing blow. So we have about 17 hours to say it. The problem is that in terms of our national grid, it depends on the magnetic field of the emission. And if that magnetic field is orientated in one direction, asynchronized with the grid, then it'll wipe out the grid. The early warning we have from that is 40 minutes. So you can imagine an interesting conversation I will have with the Prime Minister in which I say, well, Prime Minister, we have a coronal mass emission heading towards the Earth. All the indications are that it will hit us, so we're needing to take some care with polar flights and reorientate the satellites. But the big worry is that this will actually have an effect on the national grid, i.e. wipe it out. And so we may have to sort of boost the grid or turn it out, and with consequent effects on society. And he says, okay, when will I know that? And I say, well, not much before 40 minutes before it happens, Prime Minister. I'm very glad to say that is not a conversation I've had to have, and I'm very much looking forward to how Sir Mark Wolpert will deal with that issue. And indeed, one of the sort of delights of these, and I've been showing the frequency of the expected frequencies of these events, chance of volcanic eruption, a chance of an effusive volcanic eruption, a chance of an epidemic, a chance of a space weather event, and all of these have, probabilities that you can assess. They don't seem too frightening. But if you actually ask a question a different way and say, what is the chance, and I do focus it on Sir Mark Wolpert, what is the chance that Sir Mark Wolpert will have 5 years without at least one of these events happening? I'm glad to say that it comes out at a very satisfactorily small number. The chance, so essentially you move from the chance of 25% of a volcano per year. What's the chance of 5 years in a row without a volcanic eruption? It decays off. You move in the science jargon of P to 1 minus P to the n. So I've calculated, and I sent Mark a little note about it, saying you've got at least 3.5% chance of having going through your 5-year term as chief scientific advisor without having at least one of the following events. He didn't reply, actually. I thought it was slightly odd. But that is the sort of risks that we look at. And one of the things that we have a sort of bureaucracy for dealing with these events is that you will have heard of the Cobra Committee, has this image of a striking snake, the swift reaction of government. The Cobra Committee moves in. It actually has a slightly more prosaic thing, as I've indicated in the acronym, is that this is the Cabinet Office Briefing Room A, which is not quite the speed of lightning of a snake if you've ever attended meetings in there. But we have a scientific advisory group in emergencies, and I was glad to say that I'd been long enough in Whitehall to realise how important acronyms were. So when the Prime Minister, and this was Gordon Brown actually, asked me to set up a mechanism for providing have a science advisory group, I very wisely said, Prime Minister, more than happy to have a science advisory group, but in emergencies, I think. And so he agreed that. And so in one stroke, I was able to move from the acronym SAG to the acronym SAGE, thus giving the sort of import to our discussions that I thought was important. And such things are the way Whitehall can work. What we have in SAGE is we have some government scientists, we have input from industry and from academia, and for each of the emergencies I've dealt with, we have had this advisory group. It's transparent and its advice is published. People can criticise it, people can go in, and that meets and essentially reports. And the little photographic inset is to the Cobra briefing room, which is all done, and the SAGE meets and reports into Cobra and so on. So that's the sort of mechanism, and this is how we actually deal with emergencies when they actually happen. Now, the most difficult one that I had to deal with in my time was actually a combination of things, and this was the terrible tragedy that occurred in northeastern Japan with the earthquake, followed by the tsunami, followed by the disruption to the Fukushima Daiichi power plant. And what I was asked to do by the Prime Minister was to say, is it safe for the embassy to remain in Tokyo? Is it safe for our nationals to remain in Japan whilst this problem is occurring at their nuclear power plant? And so I pulled together a group of experts, and we looked at, and this is a very important concept, is the sort of what we call a reasonable worst case. And the worst case we looked at was all the reactors that were live would actually have a meltdown, there would be explosions, radioactive material would be put into the atmosphere, that would coincide with weather which was taking the radioactive material in the direction of Greater Tokyo, and that was, we saw as a reasonable worst case. It could happen. The answers when we did it, when we worked with colleagues in modelling and monitoring and in the health thing, was actually there was absolutely nothing to worry about. Even in the very worst case, the amount of radiation that would actually reach populated areas, and certainly Tokyo and the area where the embassy was tiny. I made a terrible mistake here in the sense that I likened the dangers to eating 40 bananas, and have been persecuted ever since by the banana industry, who have claimed that I've effectively ruined their business by using this analogy. I am only thankful that I did not say it was like taking a holiday in Cornwall, because I don't think I would be able to move west of Bristol after that. But it was completely extraordinary, because in fact, when we were giving the advice into the British government, and we cooperated a lot with the Americans and actually the French, at just the time we were saying there's nothing to worry about, the French were evacuating their embassy and flying all their nationals out, the Germans were evacuating their embassy and flying their nationals out, the Swiss were doing the same, a number of other countries were doing the same, and it was nonsense. There really was virtually no danger from the radiation. And in a sense, the media took this up. And just look at the sort of nonsense that we actually came. Following this, which actually had no effect in terms of anything serious, and 30,000 people died from the tsunami and the earthquake, but Germany took a decision to close all its nuclear plants, and therefore is, and I'll get on to climate change in a moment, is therefore using a lot of coal to generate its power and throwing a lot of greenhouse gases up into the atmosphere. Japan itself took a view very early on, and I think in a sense you can understand that, to do some phasing out. The Swiss agreed to phase out nuclear power. Something that really does need some scientific input. So I looked at the literature, and of course the worst disaster that has ever happened in nuclear terms, there have been others, was the Chernobyl one. And a colleague, Jerry Thomas from Imperial College, looked at the basic epidemiology here. Following Chernobyl, there were 28 deaths from acute radiation sickness, and that was entirely due to the people who were doing helicopter pilot work, firefighters and so on, who were just there. Subsequent, there had been 15 deaths from thyroid cancer. Some of children may have picked up thyroid cancer, and there is an expectation of perhaps another 60 deaths if we look at it. No problem on fertility or malformations or infant mortality, no issue on adverse pregnancy outcomes, and there's no issue of heritable effects. Compare and contrast that with the sort of hysteria that there are hundreds of thousands of deaths, which you will read about from NGO literature and read about people who are against nuclear power. Nuclear power is a question of economics and social views, and political process is fine. But the evidence points to the fact, even in the very worst case, there has been relatively small numbers of deaths involved. And in the case of Fukushima, the World Health Organization subsequently did some analysis which completely vindicated what we'd been saying, that the amount of radiation was tiny and that there's not going to be any observable increases in cancer above the natural variation. Very clear, very unequivocal. But there are some groups that do not take into account scientific evidence. This is what Greenpeace said. Greenpeace said that the World Health Organization's report is a political statement to protect the nuclear industry. It's outrageous. This is, you were talking about some of the top epidemiologists and radiation health specialists in the world working on that and trying to think about what actually happened. And we have an issue there. We've got to have nuclear power which is properly safe, because it is major disruption. But in terms of the basic epidemiology and the effects of radiation in Fukushima, nothing compared with the disruption and the problems that were actually caused by the earthquake and the tsunami. So now I'm going to cheer you up no end. Let's go back to the National Risk Register. And the ones that I've circled in yellow are ones, and I'll read them because the slide is a little unclear. It's coastal flooding, inland flooding, drought, storms, gales, heat waves, and low temperatures, including heavy snow. Those are all on our National Risk Register, and every one of them is moving to the right, i.e. becoming more likely and more severe due to the effect of climate change. And I can spell Tewkesbury, but only with a little bit of an effort. I forgot the RY. These are the sort of climate-related events that are happening. It's very difficult to attribute a particular climate event to these things, but one thing that we can be absolutely certain about, and I'll expand on that a little in the next bit of the talk, is that these elements of the National Risk Register are becoming worse. They're getting worse over time. Climate change is happening, and it is making these events both more likely and more severe. So that's the sort of short term, moving to the long term as we think about how climate affects our National Risk Register. Now I want to move to a sort of slightly longer time scale. I want to think about the world and what's happening in the world. And I make a claim here that in a number of key ways, the next 20 years are already determined. The first one, and I'll expand on each one of these, is population increase. In just 12 years' time, there'll be an extra billion people on the planet. Demography is uncertain, so it may be 11 and a half years' time, or it may be as much as 13 years and 1 month's time, but there'll be another billion people here. Urbanization, 2010, first year the urban population exceeded the rural, and the expectation is that about 55% of the world, as we go out to in 13 years' time, 12 years' time, will be in urban environments. The fourth one is a bullet point, but I think that what we are observing, and I think this is a good thing, is that prosperity, that there's a burgeoning middle-class community in the developing world, particularly Asia and South America, but also coming increasingly in Africa. And that middle classes will have desires for consuming more. And I'll come back to that in a moment. And climate change, there's important delays in the climate system, which mean that, the greenhouse gases in the atmosphere today will drive changes up to about 2030. The climate system is such it has time delays. The accumulated greenhouse gases will drive that climate change for about 20 years, and that determines the weather. So if you think about it another way, the weather we're experiencing now comes from the greenhouse gases that were in the upper atmosphere in about 1990. So if we extrapolate out, we're going to see changes in climate. So let me expand on a couple of those points. Population. First, the table gives you a flavour of it. 7 billion people in, give or take, November 2011. Probably early November or late October. Beware spurious accuracy. But another 8 billion as we move to another increase of about 1 billion by 2025. That's going to be split pretty much equally between Africa and Asia. And Africa will be where the most dramatic change is occurring. You're going to see about another 500 million inhabitants of Africa in 12 years. And that means a population increasing, and the brown shading shows an increase from about 1 billion at the moment to about 1.5 billion in 12 years' time. And in Asia, another 500 million will come, but on a population which is much larger. So it's going up from about 4 billion to 4.5 billion. And these are spectacularly short timescales to think of the scale of what is actually happening. And there's other effects that are happening. So urbanization is there. The top right points to the fact that in 2010, the urban population exceeded the rural, and indeed the world's rural population is expected to have reached a peak around about now and to be declining, whereas the urban population, the green dashed graph, is expected to increase. Thinking about the urbanization, you get some feeling that the developing world will build a city of about 1 million people every 5 days. Putting it into parochial terms, let's think about Africa. 500 million people, so 500 million people in 12 years' time extra. The expectation, because of urbanization, is that will be about 1,000 cities the size of Edinburgh in 12 years. This is, I think, completely extraordinary. And of course, the urban populations are more vulnerable to shocks, natural hazards, supply of food and utilities, and so on. And one of the things that is actually happening as a consequence of the demography is actually people are living longer, which is a good thing. But major increases in people above 65 expected in the developing world, again a good thing, but real problems in terms of vulnerability to hazards as we think about our world community. And one of the problems is that the expectation as you move out to the urban world, move out to the world into 2025, the red dots, so the very large red box, are essentially urban conglomerations of more than 10 million. Small ones are about 1 million, 1 to 5 million, and so on. I think you can see that the concentration of urbanization is very large, to a good first approximation, is around the coast. And of course, these coastal areas, particularly in floodplains, are going to be much more vulnerable to the issue of climate change and the thing that is inexorable, which is changes in the level of sea, the increase in sea surges, and other factors. So let me now move to climate change. There's a lot of talk in the media from climate skeptics. It's not happening. There is what I have termed before what I call saloon bar science. People looking out the window in January and saying, God, it's damn cold out there. What's all this nonsense about global warming? I suppose a dignification of that occurs, but not by that much, I believe. But we need to be thinking that climate change, first of all, there's no sort of killer questions or killer facts that affect climate change and our assessments of the science of it. There are millions of observations go into it. Let me just show you one. This is the deviation from what it's called global temperature anomalies. That is, you take an average period and you compare a particular year with that average. And the 3 years that are illustrated, for those of you in the back, are 55, 65 and 75. And red on that graph shows that this is much higher temperature than the average. The blue is lower, and white is about much the same. So it looks at 3 sample years, 55, 65 and 75, compared with an average of the previous couple of decades. You see a few things, like there seems to be some red up in northern Canada, which is indeed the sort of predictions that you come out of climate models, that the Arctic is more vulnerable than anywhere else in the world. But let's just look at the last 5 years. The difference in terms of that temperature anomaly, and remember this is millions of observations. This is not somebody looking out of the window of the saloon bar and the dog and duck. This is millions of observations made independently by many, many scientists throughout the world. And this pattern of climate change is, I think it speaks for itself. Now, the consequences of it, the political consequences, the economic consequences, indeed the detailed geographic things are problematic. But there is no doubt it's happening. And attempts to deal with it in terms of the climate change negotiations have been really not very successful. There was a lot of hope as we moved to the Copenhagen meeting of the parties. Hope in Cancun afterwards, then subsequently in Durban in South Africa, and then finally in Doha. And essentially it's not at all clear to me that there will ever be agreement, an internationally binding agreement. There is an agreed target, but what are targets for if you don't actually take an action? The key is whether you're going to get reductions. And it's very important, the time delay issue. Now I'm going to flip through this, it's too complicated, but I'll talk very quickly is, if you think that the weather that we're experiencing now in 1990, the weather we're experiencing now was determined by the emissions in 1990 that had accumulated. The weather that we're getting in 20 years from now will be determined by the emission accumulated to date. And as the longer it takes to delay that, the more that our climate will be altered, and therefore our weather will be altered as we move out into the century. This graph is slightly complicated, but forgive me, but basically the green bits are the scenario uncertainty. Do we act? Do we change things? There's some fundamental uncertainties in the model, which is the blue thing, and there's an internal variability. The sort of jargon is that this is a sort of climate as a chaotic ensemble. But what it's saying is, as you move out, you don't really get an effect of the scenarios, i.e. do you cut back on greenhouse emissions or you continue to increase them. You don't get an effect for about 20 years, which is the point that I'm making. Now, one of the accusations that comes about the scientific community who work in climate and working in meteorology, as they would say that, wouldn't they? That way they'll get more promotion, they'll get more papers in Nature and Science, they'll get promoted from lecturer to senior lecturer, and from senior lecturer to reader, and then reader to professor, and indeed some of them may get elected to the Royal Society or the Royal Academy of Engineering or whatever. That's kind of the snide, play the ball comments that you actually do get from time to time. So one question I posed is to say, well, what does industry think about it? Now, the top graph comes from Munich Reinsurance Company, Munich Re, And they've been looking at disasters. And I'm sorry, the key on this has not come out. But the red are essentially geological disasters. Things like volcanoes, earthquakes, tsunamis. The red shows natural disasters monitored by this reinsurance company, and there's no trend in the red. You know, God's plan for the universe is we get a rough frequency of disasters driven by geological events, which has got no trend over the last 30 years or so. By contrast, and there are a variety of weather events, and I'm sorry about there's no coding here, but the green, the blue, and the yellow all point to severe weather events which are actually occurring, which are increasing. And the economic losses, which were calculated by the World Economic Forum, are shown in the bottom thing. So industry, and particularly the industry that has got to think very hard about risk and catastrophes and the potential for natural phenomena to produce this, is saying, actually, we don't have to worry much about geological events because they're pretty much constant over time, so we can make our provisions. But in the case of events that are caused by weather, they seem to be increasing quite significantly. Of course, there's other issues to do with vulnerability. And one of the things that is really dramatic, and I'm sorry, this is the only bit of mathematics that I will show tonight, is that as climate change occurs, this is both data and also models, you have an increase in temperature or an increase in rainfall, but the variation about that increase is actually is increasing at double the rate of the average. So if the average temperature is going up at some rate, the variation in that average temperature is going up at twice that rate. And what that means is more heat waves, more cold spells. In the case of rainfall, it means more floods, more droughts, put very simply. And that variation is happening, and it's actually part of a series of observations. This paper by Hansen has documented that for a whole massive variety of different observations. Just to give you a flavour for what one of them looks like, this is the summers in Texas. The plot here is on rainfall against average temperature, and the blue dots all show essentially the last 100 years of temperature and drought and rainfall measured in Texas. That's the 100 years, and 2011 is the one that you see pretty much outside the round. Very, very low rainfall, very, very high temperatures. Now, it's very difficult to attribute a particular weather event to climate change, because these things are naturally variable. It's very difficult to do that, though you can do some approximation. And the work that the USA has done, colleagues in the USA have done, looked at that and said that if there was that climate change meant that this event, which was once in a couple of 100 years event, is probably something like 60 times more likely because climate change has happened than if there was none. So what that effectively means, you're turning a 1 in 200 year event to a 1 in 4 year event. That's the sort of pattern you have. And we have a nice parochial example. We remember 2012, the Secretary of State for DEFRA declared there was a drought in April, and no causal mechanism implicated, but we then had 7 months of the heaviest rainfall we've seen in about 50 years. And I think it's indicative to actually think about it. This was done in October by, in fact, the Environment Agency, in which a senior colleague from the Environment Agency has actually sat here. That was the current month, in October, and looking back, look at the previous 7 months to that, exceptionally high rainfall. Looking back, the previous 12 months, not quite so big, and if you looked at the average for the previous 24 months, it's pretty much pretty much the average. So what we actually have, if you ignore the monthly variation, we would come up with something. It's pretty much average in 2011-12, but actually, if you look at the pattern, it was completely exceptional, as most of us who suffered living in England during May through September, October will well recall. So intriguing, and these things we have to ponder. Now, I talked about the failure of the negotiations and the failure to actually address this. And I am really depressed about this because, as I pointed out, with the time delays, and this is a complicated graph, but basically the graph says emissions are continuing to go up, the chances of meeting a 2-degree goal are becoming more and more unlikely, and we have an issue that unless there is some decision not just to cut greenhouse gas emissions or reduce them, but actually to seriously cut them back, chances of meeting any form of target around about 2 degrees is extremely unlikely. And I have an even more pessimistic view in the sense that I find it very hard to believe that our economic system will adjust to this. Let me show you a graph there's 3 things. Let me focus first of all on the bottom left slide. The bottom left side, and you might wonder why I've singled out Minneapolis, Dallas, and somewhere in North Dakota. Well, the North Dakota, this is light. This is a satellite image taken at night of light emissions from the American continent. And by light emissions, cities, of course, produce a lot of light at night. The Bakken Formation is a major, but not the only, area for shale gas production. And shale gas has brought an enormous drop in the cost of energy in the USA. The cost of energy in the USA is a quarter of what it is in Europe. Massively affect on the economy of America to their benefit. But actually shale gas is so cheap now that actually the gas is a waste product. And this is shale gas being burned off because what they are actually after is oil, which is more valuable. So to give you a flavour of what is actually happening there, that is one shale gas bed where they're burning waste shale gas and producing enough light to be comparable with medium-sized US cities. That has happened. It's happened in the last year. This was a slide. This was taken, I think, in February by NASA. Big worry. So that's one real issue that economics will drive it. Shale gas actually has reduced American emissions because they've moved from coal to shale gas temporarily, but it's now a waste product. The second one is slightly ironic, is that part of the Arctic is vulnerable to melting, and the Arctic to heating, and there's been a lot of reduction in ice around the Arctic, particularly the sea ice around Canada, and that is opening up, and it's ironic, potentially huge Arctic resources of oil and gas. And I think it unimaginable that won't start to be exploited. They will become available with global warming, and so you've got a positive feedback that companies will go in and exploit it. I think it's unlikely that there will be this sort of concerns about environmental damage and the oil spills and so on. I think but that is unrecovered and undiscovered proper oil swells, and colleagues around here are working on that. And finally, coal. This is showing the coal reserves in the world. As you can see, the blue means lots of reserves, the white means not much, and so on, the pale blue. Massive reserves in the USA, in northwest and eastern Europe, massive reserves in China and India and Australia and South America and so on. I find it unimaginable that these reserves will not be used. I find it unimaginable. So therefore we have to be thinking about some technology which actually can make coal more benign. Carbon capture and storage is one, is saying, okay, take the fact that we're going to use a lot of coal, and take the fact that we are going to need to be, therefore, having some way of reducing the carbon dioxide. So this is going to be some of the issues that we're really going to have to direct in the next decade. One intervention is geoengineering, and I know we have experts in Bristol on geoengineering. This is just some work from the Met Office in which they looked at the potential of actually using ships to provide mist in the North Atlantic. And they said, suppose we intervened and essentially misted up the North Atlantic so that incident sunlight and energy would not actually get to the Earth. What would that happen? And they've done some experiments, slightly busy graph, and I won't, but simply explain that you have that if you do that, you will actually temporarily reduce greenhouse gas and reduce the climate change effects, but actually if you stop it, you'll recover almost the identical trajectory. Now, other interventions will be slightly different, but I think it points to the fact that we really can't be complacent about this, because geoengineering is not going to solve all your problems. And other things, and I was talking to colleagues from Bristol today, one of the other things that has happened is there's a simple physical chemical process that CO2 in the atmosphere, carbon dioxide in the atmosphere, interacts with seawater and actually absorbs a lot of carbon dioxide, around 30%. But the effect is on the acidification of the ocean. It's also an interesting way in which you can use lies, damn lies, and statistics. If you have an x-axis which is denominated in millions of years, you can show something really pretty dramatic falling off a cliff when you come down to the 20th century. And this is a trick that I've noticed the geologists use a lot. But being realistic, we have a real problem with ocean acidification. Lots of effects on marine ecosystems, on coral reefs, effects on, and coral reefs, for example, about 1 billion people depend on coral reefs for their. We need to be thinking about the reverse timescale of this, and talking to people who know far more about this than I this afternoon. The reversal effect is going to be hundreds of years. So, and as you can see, that we are probably the most acidic oceans we've had for about 25 million years. And what are the consequences of it getting worse? And it will get worse, because the accumulation of carbon dioxide in the atmosphere has not stopped, and there will be and there's nothing going to stop that. It's a chemical process. So that's the other thing to cheer you up, and I'm going to finally move and really cheer you up now. One of the people, somebody once commented that the only thing to do with a John Beddington lecture is to have a drink afterwards. And indeed, I'm glad to see that drinks are planned afterwards. The university has clearly taken the right decision. So let me move to these, and I'm going to go through these quite quickly because I think I'm slightly overrunning on time. Am I, Paul?
Just
slightly. Okay. Well, I'll go through them quickly. Look. The other challenges to the world are poverty. We've got about 1 billion people who are hungry, and another 1 billion people who don't get proper nutrition. We've got about 1 billion people who don't have clean water access, and rather more than 1 billion people who actually don't have access to appropriate energy. State of play is worrying. That essentially repeats it, but it makes 2 points that we actually are losing a lot due to weather and extreme weather, and that land has been degraded, and that we have poverty, and we are wasting large amounts. And let me move on relatively quickly. The problem is as we take people out of poverty, their consumption goes up. So the wealthier you are, the more you eat, in terms of meat, for example, or general food, or the more you want to consume in the way of energy. It's the dilemma. We need to alleviate poverty, but we need to be thinking about that, and it will affect it. And if I summarize it, the demands on the 3 key resources, food, water, and energy, the increase in demand expected out for 20 years or so from the OECD, that's the developed world, is essentially flat. For the developing world, it goes soaring in terms of the demand for energy. Much the same applies to water. There's an expected deficit going out about 15 years or so. We're looking at a 40% deficit in terms of water, and that is going to be massive. And we also have a real problem in terms of food. The deficits that we're actually looking at food, I've just used wheat and maize as an example, but many other crops would show the same. We've been pretty successful. Agriculture has improved the yields in tons per hectare quite dramatically, but if we're actually going to meet that demand as you go out, you're going to have to see a radical change from that simple linear increase. And do we need to care? Well, we need to care for lots of reasons. First of all, we'd seen in 2008, when I took over as Chief Scientific Advisor, we'd had 4 decades of declining real food prices. We had a food price spike in 2008, and about 100 million people went into poverty as prices rose. I remember at the time I said this is due to pressure from population, from consumption and so on, and the economists said nonsense, there will be a supply response, they'll plant more crops, the price will drop. And of course it did, but by 2011 you had a problem again, and wildfires in Russia and declines in productivity in Ukraine meant that actually we had the biggest increase in food prices on the FAO food index that we've ever seen. Again, why should we care? We are a wealthy country. We can afford to buy on the open market. Well, this is an interesting study which stops in 2011, but it compares food prices to political instability. I've stopped it before the real development of the Arab Spring. And it points to the fact that you get more civil unrest, more riots, more deaths from these riots, particularly in urban environments, the higher the food price is. Now, I wouldn't want to draw much more, it's a correlation, but it actually makes sense. And I think if you look at a more detailed analysis of the history of the Arab Spring, points out that we have a real issue there. So instability is generated by, it will be generated by food, this is food prices, but lack of water, lack of energy, and poverty in general will lead to instability. So to sum up, looking at the next less than 2 decades, this is the thing this is what's happening in the world. We're going to get 1 billion more people, much more people in cities, a more prosperous world, but further strain on resources, and lots of poverty still, complex demographic trends, and so on. And in terms of summing up in the table at the bottom, we need about 40% more food, 40% more water, well over 50% more energy. And if we don't do anything to alleviate greenhouse gas emissions, we're going to see something like a 40% increase. Now, it's a perfectly reasonable question to say, well, we've had all this before, the world population has increased, what's actually happening? What's happened? Beddington's rabbiting on in his usual gloomy way. But what happened what about the past? Well, actually, the past has been successful. There's a massive failure in the past to think about natural capital, ecosystems, the importance of ecosystems, and the linkages between food, water, and energy systems. So I'm very quick tour of the past. The past saw a major increase in food production, but at the expense of land. About 24% of land has actually had soil degradation. That the map shows the red is very degraded soil through to yellow, which is fairly degraded. That's what happened in the 20th century. Big increases in food production, but at the expense of degraded land. In terms of fisheries, the expansion of fisheries that occurred in the back end of the 20th century as at the expense of terrible fisheries management. And many of the fish stocks of the world are very badly managed. The red is the worst managed fisheries, the green is the best, and you've got to look pretty damned hard to find the green on that graph. And about 1 billion people rely on fish as their primary source. And forests, of course, this changes in area covered by forests. We're all well aware of the gross declines in forest cover, which interacts both in terms of climate. But in a sense, the response in the 20th century was, if we need more arable land, we cut down forests to do it. Can't do that anymore because of climate change. And the energy production, well, we all know it, increasing energy production, which has been very successful, as at the expense of very, very dramatic increases in greenhouse gas production. And water. I said water worries me. Let me take the top left-hand slide first. This is India, and the northwest India, the aquifers, the underwater supplies. Give you a flavour of it, and many in this audience know much more about this than I. Typically, water being used for irrigation in some of these areas from these aquifers is about 300 years old. So the water that has actually been used for irrigation is of the order of 300 years old. Manifestly unsustainable. And as you can see, the overexploited aquifers are shown as red, the green ones are already saline, and the blue ones are critical. The bottom left-hand thing shows some agriculture in Saudi Arabia based on aquifers, and I think the sustainability of that is pretty clear. Interestingly, Africa, with this massive expectation of population and increase in urbanization, has quite significant resources of underwater water. The British Geological Survey and others have looked at it, and there are very, very substantial resources in Africa which we can look to. But we cannot make the same mistakes that you saw in India. This has got to be exploited sustainably. And we don't actually have particularly good theories about how you exploit aquifers. It should be a fairly straight point. And we need to be thinking about smart ways to actually conserve water in agriculture and other things, and the little illustration at the point points to it. The other thing is that we have a lot of waste. The right-hand side shows the losses before harvest of some of the main world food crops: maize, rice, potatoes and wheat. Give or take about 30% of a crop is lost before harvest in the developing world. And about another 30% is lost in storage. That's the developing world. So if you're going to affect waste, you have a real chance to improve things. The developed world is totally different. The developing countries show that, transport and processing and on-farm losses. In the developed world, most of the losses are occurring after purchase, at home or in the actual process. And we are losing about 30% of our food that is actually consumed is thrown away. And you're aware of campaigns, all sort of 2-for-1 offers and so on, which need to be addressed. But that's something simple that actually could be done. So that's the past, but the real thing is the future cannot be like the past if we're going to survive in anything like the level of comfort that we have lived in, and quite often it hasn't seemed that comfortable for the next few years. We need to be thinking in terms of sustainability. We need to be thinking about biodiversity, about ecosystem services, and we need to be thinking about the fundamental links between food, water, energy, and climate change. And we need to be thinking about to do that. And the other thing that is happening is that because of the necessity that we are going to see more dramatic events, we need to be thinking about how we deal with that. And by and large, our ability as a human community to deal with threats correlates pretty much with development. And Cyclone Nargis in Burma killed about 140,000 people. Damaged in cash terms was quite a lot. Katrina and Sandy, both in the USA, slightly smaller hurricane, was a slightly larger hurricane in the case of Katrina, slightly smaller in the case of Sandy. Look at the Katrina, nearly 2,000 fatalities. Sandy, the most massive tropical storm, 200, but big damages. So development can actually do it, and one of the challenges we have for the world is to think about that. My final slide is saying up to 2050. Now, I talked about climate change. I'm not going to repeat myself again, because I just don't believe we're going to do it. I don't think we've got any chance of meeting 2 degrees. We're going to need to be thinking about it. The challenges out there are 2.5 billion more people, 70% of the world living in cities, migration to vulnerable areas are pointed in climate change happening, the basic requirements of food, water and energy, and the potential for increase with no policy change of greenhouse gas emissions, making climate change worse. All of those are the challenges up to 2050. But the one I'd like to focus on in the last moment is population. There's 3 graphs here. The top right-hand graph shows 3 trajectories. One is the most likely scenario. The central one is the estimate from the World Bank of the most likely scenario. First thing to say is the more pessimistic one with increasing children is the top one, no drop in fertility rate. The bottom one is a significant reduction in fertility rates. Notice, of course, in the point I made, that by and large, irrespective of uncertainty about demography, you're going to get another billion by 2025 anyway. The 3 graphs are almost overlaying each other. But we're at a tipping point, because the central graph has quite optimistic assumptions about fertility. It assumes that essentially there will be a decline in fertility measured by children per female, And that's hopeful. And if it does, if it happens, if those assumptions prove correct, then we are going to be looking at a world population stabilizing about 10 billion. And that's livable with. On the other hand, if you don't see these reductions in female fertility, you're looking at something like the upper graph. So half a child per female, more than the current best estimate, will take you up, but even by 2050 to 10 billion, and 30 years later by another 2 billion. Now I really believe this is a tipping point for humanity. I think it's a tipping point because there are three things that affect female fertility. Prosperity. We know we need to improve the way in which we address poverty. So we know that. But the two others, one is the education of women. And we know, and detailed sociological studies point to pretty much the more time women spend in education, the less children they have. Quite dramatic correlations through all sorts of societies. And the final one is that we know that dropping fertility means that you've got to have the availability of contraceptive methods. And those are the three key things that if they aren't there, so if we fail to get to grips with female education or the availability of contraception or indeed prosperity, we are going to be not looking at a stabilization of the world population. And I believe that moving up the 1 or 2 billion moves us into something that is, I cannot imagine, a sustainable society in 2050. However, 2050, what do I care about it? I'll be 105. 2030 worries me because I won't quite make 105. So, as I said, you are at least going to get a drink afterwards. I've depressed you all. You have at least laughed occasionally at my jokes, albeit slightly ironically on most occasions. Thank you for your attention.